All right, welcome ladies and gentlemen. This is the first of our flip lessons on enthalpy and different ways to find and or use enthalpy. So this is the video on using enthalpy in terms of stoichiometry. That's what we're going to be talking about. I'm just going to be reinforcing some stuff that we talked about in class and really explaining what it means, and then going through some sample problems, which I mean using delta H stoichiometrically. So some reminders. Now we mentioned this in class, but this is very important for this particular use of enthalpy. The units on delta H, even if they aren't written as such, are always going to be this: kilojoules per mole of reaction. Now that per mole of reaction means that the kilojoules that you're told, anytime you have a chemical equation that's shown and there's a little delta H that's sitting next to it, it means that that value of the kilojoules, that value of heat, is how much heat is either produced or consumed every time the reaction occurs once as written. That means, because the coefficients stand for moles, that delta H value is directly tied to the molar ratios that we see in the balanced chemical equation. That means that our delta H is linked to our coefficients. And we can think of very much of that enthalpy value as being for a certain amount of moles, for 2 moles or for 3 moles of something, depending on the balanced chemical equation. So for example, we have this reaction here, 4Fe plus 3O2 yields 2 Fe2O3, and we have a delta H value next to it, minus 1,652 kilojoules. Now, even though there's no per mole of reaction written next to it, it is very much there. It's implied. It means that every time this reaction occurs once, as written, meaning 4 moles of Fe combined with 3 moles of O2 to produce 2 moles of Fe2O3, we will get 1,652 kilojoules of heat being released. I know it's being released because of the negative sign. That means that that minus 1,652 is for 4 moles of that, is for 3 moles of the O2, for making 2 moles of Fe2O3. So when the reaction happens once as written, we get that enthalpy value. So we have a question here. It says how much heat is released when 1 mole of Fe2O3 is produced? Starting off with a simple one to show you what I mean. When we look at the reaction, it's asking about Fe2O3. And in the balanced chemical equation, we have 2 moles of Fe2O3. So 2 moles of Fe2O3 will release 1,652 kilojoules of heat. That is what that enthalpy value is saying. But we don't have 2 moles of Fe2O3. We have 1 mole of Fe2O3. So hopefully you understand that if we have half as much Fe2O3 as the reaction says, we're going to create half as much heat. Showing this with a T-chart, 1 mole of Fe2O3, which is the number the problem gives us, I can bring in my 2 moles of my Fe2O3 from my coefficient, and I know that the kilojoules, the minus 1,652, is for 2 moles of Fe2O3. Well, moles of Fe2O3 will cancel, and I will be left with heat, which is exactly what we want. So in this case, we're simply dividing by 2. So we get, you should get minus 826, right, kilojoules. Just to answer the question completely, and so you don't get thrown by this later, because the question is actually saying how much heat is released, because we actually do have that there, it would be correct to simply say 826 kilojoules are released. The released bit is what actually tells us that it's a negative sign. If the question had said how many kilojoules are absorbed, then the positive sign would have been implied. But in this case, the negative sign is implied through how we are phrasing the response. So that's it. That's how we use delta H stoichiometrically. That is the big point, that enthalpy values are directly linked to the coefficients of a chemical equation, because enthalpy values are for how much heat is released every time the reaction occurs once, as written. So we can use that, and we're sort of a little more likely to use it rather than just with moles, is a question like this. Given the equation, and then we have the combustion reaction for methane, and then we have a delta H value, minus 890 kilojoules per mole of reaction. How much heat is released when 4.50 grams of methane is burned? Assume constant pressure. The assuming constant pressure is really there to tell you that yes, we are in fact talking about enthalpy, delta H, because remember, part of enthalpy's definition is that it's the heat exchanged in a chemical reaction under conditions of constant pressure. So that's actually hitting part of the definition of enthalpy. Again, this minus 890 kilojoules, because this is per mole of reaction, and it always will be, even if it's not explicitly written, means that when 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water, 890 kilojoules are released. That is what that value means. That number is directly linked to each and every one of the species in this chemical equation. In this problem, we're given 4.50 grams of methane. So that's where we want to start our math. Hopefully by now, you feel very comfortable knowing that, okay, the problem gave me grams, I should turn it to moles. Hopefully by now that is starting to become a bit of a reflex for you, which is great because that's a necessary reflex in AP Chem. So our gram formula mass of methane is 16. Right, 1 mole of methane weighs 16 grams. So I'm just using my GFM here to convert grams to moles. And the reason that I'm doing that, again, is that 890 is for moles of things in this balanced chemical equation, not grams. So I do need the moles. That gives me moles of methane. It's asking, though, for heat. So I want kilojoules. So now I'm going to look at my coefficient for the methane. And I'm going to put that on the bottom of my T-chart right here. That is my coefficient. That's why it's 1. It could be something else for a different reaction. And then my 890 kilojoules is going to go on the top. That's the 1 mole of methane as shown in the balanced chemical equation. When it combusts completely, you will get 890 kilojoules being released. So now it's simply this math of 4.5 grams of CH4 divided by 16 and then multiplied by negative 890. You will get a negative number when you do this. You'll get minus 250 kilojoules. So we can say 250 kilojoules are released. You could absolutely leave your answer as minus 250 kilojoules. That would not be wrong. You could also make a statement about whether the kilojoules were absorbed or released. They're both correct. They're both saying the same thing. They're both including that direction statement in the quantity of heat, which is the most important bit. Now, this answer, 250 kilojoules, this should make sense because 1 mole of methane releases 890 kilojoules of heat. Well, 1 mole of methane weighs 16 grams. We don't have 1 mole of methane. We have 4.5 grams of methane. That's about a quarter of a mole of methane. So we're not going to get all 890 kilojoules being released here. We're only going to get about a quarter of that because 1 mole of methane gives us the 890. So a quarter moles of methane will give us about a quarter of the 890. And that's what we're seeing with that answer. And then one more problem. Hydrogen peroxide can decompose to water and oxygen by the reaction. 2H2O2 liquid decomposes to 2H2O plus O2 gas, and we have a delta H value. Calculate the heat evolved when 5.00 grams of hydrogen peroxide decomposes at constant pressure. So again, very similar problem. 5.00 grams of hydrogen peroxide. Convert that to moles. So we're using the gram formula mass here of hydrogen peroxide. This is our GFM. And that gets us moles of hydrogen peroxide. But we want heat. Calculate the heat. So we want kilojoules. Well, kilojoules are here, but this number is directly tied to each one of the coefficients. That number is for 2 moles of H2O2 decomposing to 2 moles of H2O and 1 mole of O2. Well, in this case, we have hydrogen peroxide. We have H2O2. So, using the coefficient from the balanced chemical equation, we know that 2 moles of hydrogen peroxide release 196 kilojoules of heat. So we can plug in and get our units to cancel. And when we do that math, 5 divided by 34 times 196 divided by 2, and we have a negative value, we should get minus 14.4 kilojoules, or 14.4 kilojoules are released. And that's it. That is the idea behind using delta H stoichiometrically. That is truly it. This concept that delta H value is directly linked to our molar ratios. That is all it is. So you'll be doing some practice problems with this in class when I see you next.